So now, to look deeper into the fact that the moment is always equal to the force times its perpendicular distance, let's look at this beautiful picture here, where you can see the wrench again and the hand that pushes on it, but this time the hand is actually not pushing parallel to any axis. It's actually pushing at a random angle theta. So to clarify that, let's add our 3D coordinate system again. So I have my y-axis here and my x-axis is perpendicular to that. So here's x and here is y. And now I have a problem here because this force is not parallel to the x or the y or the z-axis, it's actually random in space. To clarify how I'm thinking of this here, let me just clarify that this is a force in the xy plane, right? So it's acting in the xy plane, and therefore it's not parallel or perpendicular to anything. In real life, you would never do this because you intuitively understand this formula already. So you would never waste some of your force component, as I will show you in a second. You understand that your lever arm has to be perpendicular to your force, or you might as well say that M, and by the way, it's about a point always, is equal to F perpendicular times D. So it doesn't really matter which one is perpendicular to one. Of course, it's the same. If the force is perpendicular to the lever arm, then the lever arm is also perpendicular to the force. But let's understand that here we do not have that scenario. So what can I do? And what do you usually do intuitively in real life? You actually would apply your force automatically perpendicular to the wrench. And so I can actually symbolize this here, and I can add the force components. So this blue force has two components. It has a perpendicular and a parallel component. So let's say I have a parallel component right here. And then that, of course, must be pushing in this direction. And I'm going to call this Fxy perpendicular to D, right, if you will. So this effectively means that we're looking at Fx, right? So we get that Fx component. And I, of course, also have a parallel component, which I can draw into two places. And I do that for you because you would probably think that it applies here, which then would be acting at this point, and this would be Fxy parallel. But I think it's better to draw it up here because it shows us that we actually have the right angle here, and then we can also call it Fy. And again, intuitively, you already know that this force component is really what causes the rotation about this point. So you would never waste this part here. But if you were to do so, what can you do to really calculate this or to really end up with the right numbers here? You would pretty much calculate Fx by stating that Fx is equal to Fxy times sine of theta, right? So because the theta is actually on the opposite, or maybe let me make that clear here, we have theta here as well. And therefore you can use the sine function for completeness reasons, although we don't need it today. Fy would be actually equal to Fxy times the cosine of theta. However, what can you do now? You can now calculate the moment of your force at a distance dy, right? Let's do that. So let's take the moment here and calculate the moment, in this case about the z-axis, which would be equal to Fx times dy. But we just rewrote Fx as what? Fxy times the sine of theta times dy. And what we said is that this here, this component, is really F perpendicular. And therefore, you probably remember that you used this before and you calculated actually 3D moments in your physics class before. And the way that was done was you were giving a formula to calculate the moment with the double arrowhead. And this actually only gives you the magnitude. Remember, we're talking about scalars here today. But what you were given is r vector cross f vector. And now if you remember your formula properly, then you may remember that it was nothing else than r magnitude times f magnitude times sine theta. That is one formula you can use to solve cross product problems. And now the question is, why did this work? Of course, you know this already because you follow my logic here. It works because fx sine theta has created the perpendicular lever arm. And the perpendicular force. And the lever arm is just r. So what I have done here is turn this into f perpendicular. And that is the reason why your cross product formula actually works to calculate those moments in 3D. And we will use this in the future a lot. But for now, let's just state here that we have rotation due to the perpendicular component. This is very important that you understand that it's always due to the perpendicular component. And let's write a conclusion sentence here, or concluding sentence. So in conclusion, the lever arm must pass through the point of interest comma, while the lever arm must be perpendicular to the acting force. Otherwise, you waste energy, if you will, or you waste some of your force components. So in conclusion, or as a result of that, if the force is not perpendicular, so if force is not perpendicular to the lever arm, either the force or the lever arm must be converted into the parallel and perpendicular component. And of course, to use the perpendicular component. You won't need the parallel component for this. So please understand those two concepts. That's what we are trying to show here with this nice picture here. And again, I, in this case, used the perpendicular component of the force, but I also could have kept the force in its original form and then just turned the lever arm into its perpendicular component. Just for completeness, let me zoom in on that one and show you how that would look like. So I could have, for example, found a point where I end up with a right angle here, and then I would call this R, and I could also find the force times that distance, but that distance R here, based on the geometry given in this picture, because I was given this angle here, would have been a waste of my time. So it was easier to talk about it with the force broken down. But it doesn't matter if you take the force or the lever arm. You can always turn that lever arm. All right. You can always turn both, I should say, into the perpendicular component. So that concludes that portion. Now let's talk about the multiple forces. And what you see here now is a two-dimensional coordinate system, x and y, with three forces that all rotate about a specific point. So you can already tell that F1 rotates from positive x to positive y. Therefore, it's turning counterclockwise. F2 turns from negative x to positive y, which makes it clockwise. And likewise, F3 turns from negative x to negative y, which makes it counterclockwise. And remember that counterclockwise is actually considered positive, right? And you can always remember this from your first quadrant. From x to y gives you positive z. So that is how you do that. But what we're trying to talk about here is that force systems can be summed up, right? As long as forces times lever arm act within the same plane, and about the same point, they can be summed up. So what does that mean? So an engineer would say the sum of the moments about point O is actually equal to, and let's take a look at these circles here first, or the semicircle, or the portion of the circle. So M1, M2, and M3. So the way I would write this is plus M1, right? Because it's counterclockwise, minus M2 because it's clockwise, and plus M3. And let's just say that moments are counterclockwise positive. That is something that we definitely need to highlight. So let's go ahead and do that. This is something you need to understand. This is because of the right-handed coordinate system, right? So due to right-handed coordinate system. So because of the right-handed coordinate system, we call moments positive if they are counterclockwise. And now I can complete my formula here on the bottom. I can also say that it's plus F1 times D1, which is the perpendicular distance, of course, right? Minus F2 times D2 plus F3 D3. And that is what this picture here tells you, because we are finding the moment about point O for all of these forces that all act in the two-dimensional plane. We can actually sum them up, and we can just do the mathematical sum for force times lever arm. So really what you will see later on is that the sum of the moments about a point O, and since we're talking about 2D, it will always be about the z-axis, is equal to the sum of F times D perpendicular. And of course, we define counterclockwise positive because that's mathematically correct. And now we highlight this because that is an important concept to understand, especially for your upcoming homework, where you actually have to sum up different moments. So that clarifies how we find the moment for multiple forces that rotate about the same reference point. And the key word here is the same reference point. And of course, they have to be in a planar system, which here I identified with xy. And therefore, our moment will always be automatically about the z-axis, and it will always automatically be counterclockwise positive. This is a definition you see over and over in this class, so you might as well remember and understand this right now, because you will see this a lot in this class later on in a different context, and it is my experience that students often struggle with that. But if you already get familiar with what we talked about here, it should be a walk in the park for you, and I believe we can now conclude this page because we have all the information that we need now to put it to an example and to apply our knowledge so that we can solve problems as we see them in the real world. Let's move on to our example problems.